Thank you so much, Rebecca. And thank you all for who have gotten here already. I just wanted to do a brief introduction to myself to start things off here and maybe allow a couple more people to come in. So as it says on the screen, my name is Katrina Van Duzen, and I'm a senior ecologist at Great Ecology. We specialize in creating and augmenting wetlands. And today I want to talk about something that's near and dear to my heart, which is basically bioretention and how to create methodologies that will remove forever chemicals and stop them from cycling in our environment. I've been here with Great Ecology for approximately a year. However, I have about 20 years in the remediation industry, spanning the country. So I've worked all over the country, and I have been pretty much focused on bioremediation for the past dozen or so years. And bioremediation and phytoremediation we're going to talk about, and I'm going to define everything for everybody. We're going to use this as a learning mechanism so that you can be very cognizant of what I'm speaking of later in the presentation, where I go over how we can use this to basically remove the forever chemicals. So without much ado, I'm going to basically continue here. All right, so as we are well aware, stormwater is a combination of water that basically has many different chemical contaminants and pollutants in it. Now, some of these pollutants are the forever chemicals. And when I talk about forever chemicals, I'm talking about chemicals that are compounds that usually are recalcitrant to degradation. And that means they don't break down very easy. So two of these that are the primary bad boys, let's call them, are PCBs, polychlorobiphenols, and the PFAS family of compounds. And, you know, they basically find their way from spills that occur on terrestrial areas, also in water, and they get into our world's surface water through stormwater systems when they get redirected. And basically, once they are in the system, they cycle throughout the air, water, and even ecological receptors almost indefinitely for many, many decades. Let's see. I don't think I have the capability of letting people in. All right, great. So basically, what are we going to do about these? We can't just keep allowing them to get into our systems, because what do they do and what harm they cause is the real problem. So we need a solution to prevent this cycling through all of our systems. And we all know as stormwater professionals that loading of contaminants from non-point sources into the surface waters is one of the primary problems. And, you know, those horrible TMDLs and trying to achieve them is very difficult when we have high amounts of these pollutants coming into our water. So one of the things I've been working on for the past 10 years is how to keep them from entering into the surface waters and other receptors, rivers, ponds, oceans, and making their way even into our stormwater systems. So how do you do that? Well, I've discovered a way, and let me just go on. One of the things are PCBs and PFAS compounds that find their way from spills into our world surface waters, and then they cycle through. We've talked about that. And so we need the solution. And one innovative solution is phytoremediation. Okay. What is phytoremediation? It is a form of bioremediation, and that it uses plants and algae to contain, remove, or somehow render environmental contaminants harmless. And I'll get more into how it does this. Okay. So what are the capabilities of phytoremediation? Because you're probably asking, well, how can plants do this? But they really, actually, this has been very well documented in over 30,000 different papers, how they can remove different pollutants, minimize soil erosion, reduce transfer of toxic substance into the sediments, soils, surface water, groundwater, in both in situ and ex situ applications. Okay, so what can they work on? Well, there's a whole list. And again, this is based on all of the research that has been done since about the early 90s on what kinds of sites they can work on and what types of contaminants they can work on. And as you can see, the list is very large. So metals, for example, agricultural nutrients, orthophosphates, even radioactive particles, wastewater nutrients, organic compounds, and this is where you come with your PFAS, PCBs, CFOCs, PAHs, and post-remediation residuals. This would be an example of a brownfield site, okay, which has, you've done a lot of remediation on it, but you still have enough of like the typical brownfield contaminants, but they're just above the action levels and you still have to do work on them. So what types of plant species? Now, I don't want to just say that they're only macrophytes because it does include algae and bacteria in this, but because I consider that more of bioremediation, I like to break it out into macrophytes that are used. And now you're not restricted. You have upland meadow species, you have grasses and reeds, you have trees, legumes, even transgenic species. Then you have your aquatic hydrophytes and even xeric and halophytic species. Again, it's based on what the site has and all of the considerations that you are looking for. You have to, understand in terms of restoration practitioner values, how much sun do I get? What's the pH of the soil? How much water do I get? What is the type of precipitation? Is there additional surface hydrology vectors that are coming into your site that you want to take advantage of? And then this decides what type of species you will use, because the desert species and the wetland species are two different species, but both of them might be used in a way to remediate metals, for example. Okay, so what types of matrices if you're working with it? So actually phytoremediation pretty much works in everything if you have the right species. Again, that's a plant species that I'm talking about here. So soils, surface water, sediment, and groundwater can all be media or matrices that they can work on in situ. And when I say in situ, that means that I can plant things in these environments and they'll work on that substrate, okay? Ex situ would be something different. People say, oh, well, this is too new. There's not a lot of background on this. And actually, that's not the case. In fact, this goes back as far as the Mesoamerican city-states, such as Tikal, where stormwater was shunted, and they're calling that an example of phytoremediation because of the plant species they used and some of the engineering applications that they did to do this. In Germany, it was used to treat sewage 300 years ago. And then in the United States, we began with the impetus of SARA Title III is starting to look at plants as a way to uptake contaminants. Now, believe it or not, is the #1 strategy for remediation because of its price component. We'll take a look at that in future slides. Okay, so why the EPA is actually one of the biggest promulgators of phytoremediation, and we can understand that. They're working on Superfund sites. It is the lowest by far in terms of remediation costs to use this type of methodology. All the other traditional excavation, in situ chemical oxidation, thermal desorption, all work, but they cost so many millions of dollars compared to the thousands of dollars that phytoremediation costs. Now, you might say, oh, well, that's the EPA. They're just trying to cut costs. But I've used this in many states across America because their environmental departments want to find a low-cost solution that actually works instead of just leaving areas fallow. And they actually approve this strategy in most of the states. And another thing that I've come in contact with, as I'm sure you have as professionals, environmental professionals, is will the pollution insurance carriers, if there is a pollution liability clause on the site or an insurance package, will they accept it? And I have successfully argued that it is a viable remediation strategy and they will approve and accept this as well. So what kinds of processes are associated with with phytoremediation. So you may say, okay, well, what are the ways that plants can break down these contaminants in the environment? And really, it is a function of the plant's metabolism, its morphology, in other words, where things get stored in the roots, in the stems, in the shoots. Can it metabolize it? In other words, can it create an environment where it basically takes the original compound and then breaks it up into inert, harmless ingredients? And these are all the different types. So rhizodegradation, and I will get into each of these and what they do. Phytohydraulics, phytoextraction, phytovolatilization, and phytostabilization. So let's take a look at these in a little bit more detail. So rhizodegradation, this is a very go-to strategy for wastewater treatment. In other words, when they use their settling tanks, some of the settling tanks can actually have plants in them. And what happens is that they use the roots and the bacteria in the roots to basically break down some of the contaminants, or even to absorb a lot of the nutrients in the wastewater. Okay. This is especially good, and I'll talk about some sites that we have done this on where they have used this. I use this as is in the capacity at NJ Escort, where they were trying to basically have the astronaut wastewater remove all the pollutants so that they could do the mission to Mars, which unfortunately was unsuccessful. All right, so what about phytohydraulics? That sounds pretty cool. So phytohydraulics is basically using a tree's root system to capture a plume. Now, this works on both floating or L-napple plumes or D-napple plumes. So basically, it has to be in contact with the roots of the tree. Now, I've also used some systems which use what they call tree wells, which means that they have the tree roots cased off until it comes in contact with the correct groundwater aquifer. This allows you to punch into different aquifers, and it basically removes the contaminants as well if the contaminants can be metabolized by the tree. How much trees do you need, you're going to say? Well, you can use it on a perimeter if you carefully calculate out how many gallons each of the trees can absorb. For example, a lot of people don't know that Salix babylonica or a willow tree can absorb 25,000 gallons of water during the summer months. Now, you can also mix the species up, which is what I often do on the eastern seaboard areas, so that this machinery of using phytohydraulics doesn't just shut down. It basically continues in the winter by using coniferous species of trees. So what does phytovolatilization mean? In this case, you're talking about a plume of wastewater that's located in an upper aquifer that contains something like a CVOC, which is a chlorinated volatile organic compound. These are notorious, as many as you know, not breaking down in the environment, especially when they are segregated into anaerobic areas. So trees, especially poplar trees, can be planted and they can absorb this plume, and they will basically take those CVOCs and turn them into inert organic compounds, and then you don't have a problem anymore. On one of the sites that I use this, they had basically gotten down to the 2-chlorine or cis-DCE, 2,1,2-DCE, and they couldn't go any farther. And it was 20 years of this. And so what they did was they had many people come in and they said, oh, we need $5 million to install a pump and treat system. And I installed the system of trees, and the plume went away after 3 years and no longer was a problem. There was no effluent produced. There was no pump and treat mechanical equipment required. And the client loved it that he had a campus-like feel now to his former industrial site. So what about phytoextraction? Now, you'll see a lot of this in hyperaccumulators, especially in wetlands. And that's because a lot of them, that's what their purpose is as wetlands, is to absorb a lot of these contaminants. not that nature made it like that, but that's what is coming up now is that, oh, wow, they're great for this. So two of the things that they've already proven is, of course, metals, but most recently, PFAS. And this is one of our treatment wetlands called the Del Mar Fairgrounds here, located in California, in sunny San Diego, for those who are not in California. Phytosequesterization. So this is usually associated with roots and microbial fixation at the root nodule level. This one I like to use is, the good example for this is mulberry trees, which have an affinity to absorb PCBs, which you can also, another compound is very hard to degrade, and you want to basically just sorb it and leave it and not have it migrate into other pathways. Okay, so what types of applications would this all be good for? Now, there are many applications of this. I am just going to give kind of a broad overview here and then go into what we're really looking for is stormwater bioretention. This is exceptionally good for ecological receptor sensitive sites. So you have a site and, oh, there's a special little frog or a special little toad or whatever might be there, and that becomes a sensitive, threatened, endangered species, and I can't do any kind of traditional excavation because it would disturb the environment too much. Agricultural runoff with vegetative filter strips. We also have wastewater and mine waste treatment, which I'll touch on. Again, I'm going to mention the plume control. I've had a lot of success in this on the East Coast in areas such as New Jersey, where there's lots of groundwater aquifer plumes that are contaminated with dry cleaning and gas station contaminants. And then we're even going to extend this now to living shorelines and what protects us in the future from the natural process of climate change and, you know, storm surges that are hitting our coasts, as well as the increase in the stormwater velocity and the velocity of the surface waters, rivers and streams, and causing massive erosion. So think of it in both of those capacities. All right, so let's go to the first one, which is very important in areas here in California, in the Midwest, even in New Jersey and Pennsylvania. They're starting to use what they call vegetative filter strips. Now, this is a function of identifying where you have large areas of just sheer water coming off, your sheet flow coming off, and not having anywhere to go. And then it goes right into the stream. So if you have a source point, such as a golf course, a park, a farm where you're using lots of fertilizers, and you don't want to have all of that, all of the sediments that have these contaminants or just even fertilizer or orthophosphorus, you can basically create a perimeter vegetative filter strip around your property, or you can create it next to the surface water outfall. So that would be something like a stream or a river. And we had success with this in industrial areas that have high impervious surfaces. You know, we're talking 90% impervious surfaces, and shunting all of that, precipitation into catch basins that they go directly into rivers. So what can you do? So by creating these vegetative filter strips, you can actually remove a lot of the sediments. And the sediments, of course, high loading, high to dissolve solids, but it also has pesticides, herbicides, nutrients, and other accumulants such as PAHs and metals. Again, ecological receptors. So any place that you have a magical species on it that needs to be protected, my coworkers are laughing at me, and you need to protect the species and not do very ground disturbing things, this would be the greatest area for this, because you can plant plants and they will remediate the area, but you don't plant them in a biomass with a monotypic stand so that they then eat the contaminants. That's a very important fact that I will make more clear later on. So floodplain restoration to create living shorelines for storm surge buffering, I'm going to also include this in here because that has a lot to do with what's going on in the future. And we see this a lot now in New York, where we're having a lot of storm surge buffering going on on the East Coast properties, especially parks and other areas at confluence of rivers such as the Hudson. And this is what I was speaking of before with your LNAPL and DNAPL. And what I like to do with this, if it's a large site and it's been fallow for a long time and they don't have any plants for it, that's great. You can plant trees all over it, but that's not usually practical, especially with you know, city sprawl and everything else. So perimeters, I created inhibition perimeter, I call, because some of it gets through, but most of it doesn't. If you calculate the number of trees in a density and have enough space to do it. And this is great for properties that are abut a sensitive receptor, such as a wetland or a stream. In other words, instead of having all the parking spaces, you take a certain square footage and you make it a tree line, and you basically put these species, and if it is a floodplain, you can use also wetland species, and these species will prevent that plume from going into the sensitive receptor all the way. So that's how it inhibits it from the plume inhibition factor. So another thing, we have about 800 mine sites here out in California. And the history of mine sites is that the mine sites that have been created by the Romans 2,000 years ago are still contaminated. And those are, you know, low pH soils because of the acid mine drainage, and also high in metals because of the leachate. But these are also like wastewater for wastewater treatment. If you can't get down to your TMDLs, you might want to think about incorporating some bioretention strategies in terms of retention basins that have plants in them to remove things like nutrients so that you can meet those TMDLs. You can also basically create a in situ vegetative cap that basically combines remediation and restoration. In other words, you use plants that have the ability, for example, at a mine, to not be affected by the low pH or the high metals. And those plants then do well where everything else dies. All right, so let's get on to stormwater. Now, stormwater has made dramatic changes, and I would say the past decade, in terms of how they're viewing everything about stormwater, like how to decrease the flow of water so that it doesn't cause so much erosion, and also how to decrease the amount of contaminants. What does that look like? And you have heard of stream daylighting. Well, this is almost like a function of that. And the U.S. Army Corps of Engineers over the past, I would say 15 to 20 years, has done a lot of evaluations about hardscaping versus softscaping. And all that means is using culvert systems and hard bottom concrete systems for retention and detention basins instead of using wetlands and other what they call pocket wetlands and other modifications, which I'm going to show here today, which is now called bioretention. It's a fancy word for saying I am going to do stream daylighting and create pocket wetlands or some other function of that. Because they basically decided in many, many studies that a large source of the contaminants are coming from, unfortunately, the point sources in our stormwater systems and getting into our overall aquatic systems, which is streams, rivers, and oceans. But again, this is also for non-point sources arising from stream flow that's just coming in. But the largest one, the greatest source, is our point sources from stormwater systems. And if you want some more information on that, you should look up there a lot. They have tons and tons of papers on this aspect alone. So what do we do? How do we basically change the way we've looked at these things in the past? Instead of looking at it as an engineered system just from a simply detention basin or retention basin and a culvert and a hardscape, what do we do? How can we use our existing infrastructure and change it so that we can use the best management practices moving forward to retrofit these systems with bioretention strategies? And these potentials are, as I outlined here, detention ponds, outfall pocket wetlands, you'll hear the term, retention pond, retention trenches, and lagoons. And you'll see these cropping up, and you may not even notice these, but let's say they take out a central median and now there's plants in them. Well, a lot of them underneath those planting things have a filtration system that then goes into the stormwater system. And that removes a lot. And I'll show you how much it removes. So here is a typical retention basin, I believe. And this was a hardscaped option. And what they said is, let's take these structural stormwater point source and do a bioretention retrofitting and test these. And what they found is that a dry pond, and what they're calling a dry pond is basically just concrete, okay, has 10% removal efficiency, because basically the first flush, it goes right out. But a wet pond with extended detention, in other words, a thicker, deeper pond that's sitting around and allows the sediments to settle out, increases to a 60% removal rate, which is pretty good, right? But when you replace that same system, that same detention basin, with an engineered wetland, it is increased to 80% removal efficiency. So now we're getting into numbers that actually are significant. So what does that look like? So here's an example of PCBs. When you do this with PCBs and create using phytoremediation plants, they are sorbed and sequestered in soil, which is a fancy word for they get locked up. That means that they no longer get reintroduced into the environment. And it basically acts as a net or a catcher's mitt, if you want to call it that, so that these chemicals, PCBs and PFAS, are no longer getting reintroduced, and they're getting removed from your TMDLs. Now, PFAS is very new, and there's not as much data concerning them, but the data that's coming out is that they are very similar in terms of loading into the soil, okay? And you can see that as things come in, it basically loads, and then it doesn't let it come out as much. And what does that look like in the overall? We have a 90% removal of PCBs when we use this phytoremediation strategy, in addition to the pocket wetland, which is Army Corps of Engineers' new best practices for the 21st century, moving towards municipalities upgrading their systems to bioretention. Now, of course, these are very nice and fluffy dreams, but this is kind of what their goal is, like getting the removal of contaminants from sediments and the loading decreased through different new innovative strategies. So by retrofitting existing stormwater infrastructure, we have 90% removal of the worst offending species of compounds. Now, this is very similar for PFAS, and for those of you who aren't as familiar, because they are new things, they come from pretty much everything. They're very much like PCBs, but one of the very large source of it is just basically spills and landfills and various industry point sources, but also things like firefighting foam, which we've been using for years, without any constraints, thinking that they were great. And they're just emerging now, but I believe that they've been emerging for the past 10 years as a possibility of a potential compound. And the reason why is now they're thinking that they may cause problems with ecotoxicity problems. And that's why they're looking at them more towards the human level and their exposure. Because obviously once they go into the aquatic environment, they work their way up through the food chain. We eat the fish or ingest water that's contaminated, and then we have problems. And we can only say at this point that they just suggest, because it's very difficult, as we know as scientists, and to remove, there's cross-contamination issues. Which one is actually causing this? But it looks like the studies are now pointing to public health effects from PFAS as well. And, again, they are just recalcitrant degradation. They don't want to go anywhere. And we're finding them all over the world because they just cycle like this throughout all of the environments in our biosphere. And they just really most of the biogeochemical processes that break down other compounds and the microorganisms will not work upon them. And that is the big problem. And we know that unfortunately the traditional remediation doesn't work. You can't excavate them out. Even activated carbon usage, it does it for a short term and then they're right back. So what we can do is start thinking about them the same way we think about PCBs and the success we've had there, and use bioretention retrofitting within our stormwater systems as one innovative strategy to remove them through use of phytoremediation species. And this basically shows you like how they get locked up into soils. But the problem is that if you don't have anything breaking down the soils, then you're going to have huge loads, and then those soils have to be remediated. And by using plants, that breaks down the compounds or in some way metabolizes them so that they no longer can re-enter, and they don't have to be, the soils don't have to be remediated themselves. And so the number one is bioaccumulation, okay? And this, I think, diagram shows very nice how all of these are broken down, all the different substances, and then how phytoremediation will actually transpire them into the air. Now, this can be used also in the water, which is what a pocket wetland basically is, using emerging hydrophytes. The problem I have with the root uptake of PFAS in just soils alone is that it's a slower process. With water, it's a faster, but that may change over time as they do more and more research into what species are the best for this. Okay, so now I'm going to kind of give you an overview of the phytoremediation and how it works. And, this should help to kind of button things up in terms of what we're actually thinking about. So what are kind of the pros of phytoremediation? Now, the phytoremediation, when you use plants to restore or create a wetland, it's not engineering in the way that we have to have large maintenance and large installation costs. So usually it's around, between 10 to 25% of what a normal, the same site would cost to do more invasive remediation, such as thermal desorption and excavation and in situ chemical oxidation and all the rest of those very invasive substance processes. Even when you consider pump and treat, these are all millions of dollars a year to then treat the soil or treat the effluent or treat the product. And that's one of the key things, is it runs on solar power. So there's no energy requirements. Okay, you don't have to keep a machine moving. You don't have to keep pumps. You don't have to repair the wells from pump and treat or maintain them. There are no effluent streams. There's no soil to remove, transport, and treat or dispose of. There's no water. So that's a very important cost differential for long-term sites that have been contaminated for many, many years. Now, once you get the right dynamic of plants, what you want to do is create a dynamic equilibrium of plants that's normal to the area for that wetland or forest or forest, whatever the environment is. You have to use species that are normally there, but that have the potential. And that's a matter of the scientist or ecologist picking out what species work, what are there on site already, and what can be used in the future. The other pro, I think, which is very good for redevelopment purposes in cities and suburban areas, is that it's an aesthetically pleasing option. When I'm creating a pump and treat with trees, this looks great on a corporate campus. This looks great on a school. I don't have wells and giant baker tanks and people in white hats running around and vests scaring my neighbors. So these are excellent for high profile sites where you don't want to have that component. And every municipality loves this. All the school systems love this. This is a win-win strategy for everyone. No one is against this ever, at least as far as I've been a part of all the projects. They all want this because this is a very positive outcome that actually treats the soil or groundwater or sediment without making a big to-do. And especially when you have sites that have been, just sitting around with a concrete cap on them, and they can't be basically used ever again. So it's an excellent form for that. Now, one of the main things that people have is, oh, well, then you have to remove the plants. They're going to accumulate too many contaminants. That's not the case when you use a mixed palette, we call it, ecologically. Instead of just one species, let's say a hyperaccumulator, like a brake fern that's going to accumulate metals. Well, I'm not going to plant them across the site. What monotypic stands often imbalance the system incredibly. Yes, they're good, but they become invasive in certain situations. And they also then start to achieve biomasses that require removal. Okay. And so it has a lot of great perks to use phytoremediation, even in stormwater systems. Using these in conjunction with a firm that can make them look pleasing, that won't incorporate a lot of invasives, you're going to have a good effect that people will like to. And one of the places that I use this is retrofitting a stormwater basin and a culvert system and a stream to create, after that, what was a smaller wetland surrounding, next to the stream, and then putting in a walkway so people could use it. And this allowed the viewing of all of these birds and species that came back to this area. And it was a treatment area, and nobody even realized it. The birds became so prolific that they increased the biodiversity of this area. So everybody was happy about this. So again, I just touched on biomass. The one problem is when people plant transgenic or cultivars that are very, very sensitive. So invasives can take over if you don't know what kind of mix to use, and fight fire with fire, we like to say, in terms of roots and growth, heights. All of the gardening, let's say, environmental resistances that you come up with in designing a large garden have to be accounted for. And that's where specialization in ecological restoration really is important. Oh, sorry. So we also have climate constraints. I talked about this a little bit. If you have only a couple seasons where plants grow, well, then you have to account for that with using conifers. Plants are limited based on their root depth. You have to know where the contaminants are. If they're down low, you have to use trees versus grasses, that type of stuff. And the surface must have some sort of interface that you can plant in. Now, this does not completely restrictive. If you have a parking lot, you can make planters that are actually connected to the subsurface soil. So it's not completely restrictive. So what about bioremediation? Well, the global market is expected to explode because everybody across the globe is actually using this. It's the only thing that can really take on countries that don't have enough money to do millions, hundreds of millions of remediation. So they are picking up on this. And you might have seen Chernobyl planted 1 million sunflowers, right? Well, sunflowers can accumulate radioactivity. So people are doing this in different ways. And you can see that they are projecting a $13.82 billion market, with a huge component of that is basically phyto. And it's projected to grow over the next 20 years, especially with all of these various municipalities across the United States starting to do bioretention retrofitting. So phytoremediation is cost-effective, sustainable, versatile, innovative. In fact, in some states, there are certain allocations for using innovative remediation technologies that this qualifies for, because it's still considered newly developing technology. In other words, even though they've had it around since the 80s, the application of it is so selective and requires a high level of analysis that many people don't use it when they really should be. And for stormwater, it removes sediment 75 to 90%. 90% is when you use phytoremediation species. 75% is basically for your average pocket wetland. Okay, so I'm going to go over a couple. I think I have time to go over a couple of projects that we have done here at Great Ecology, which is my firm. And we, as I said before, we specialize in creating wetlands. These are treatment wetlands, but also restoration wetlands, storm surge, and living shorelines. So we can basically do this for high nutrients, high fertilizers, again, 50 to 75% just nutrient removal. and it operates at a much lower cost than a traditional treatment system. This is the Del Mar Fairgrounds, and you can see that the fairgrounds didn't want to put a big treatment system here, so they put something that looks nice, so it's aesthetically nice. Here's another example. This one was in Denver, Colorado, and this one we redesigned to, again, treat the stormwater sheet flow that was coming off of this park, and we used a native plant palette in this case that basically could absorb a lot of water. And all of the features of this were very aesthetically pleasing, even though it was ecologically designed. Again, in Denver, Colorado. Now, this was a little bit different of a site because in this site, the down gradient houses were in a floodplain, and all of the sheet flow from higher areas was rushing down and basically flooding out all these houses. So there was a brownfields project, and they decided to try to create a seed mix using the native grasses, which, if you don't know, are becoming somewhat rare to use this. And it wound up absorbing the stormwater and not causing flooding for about 100 different houses. Okay. And this is what it talks about here, is the 100 homes were saved from having to get flooding. And we designed all of this. Now, all of these projects that I'm mentioning, they're actually all, in one way or another, award-winning for innovative strategies. So as you can imagine, we have a lot of great design ideas for whatever type of system that you're trying to work on or that you need a solution to. In this case, this is more of a stream daylighting project, I would call, where they just kind of decreased the stream velocity through a bunch of different ways. And that was the creation of dechannelization, as well as increasing rock formations within there, and also allowing more of a plant riparian area that absorbed more of that. Again, a lot of modifications that increase the stormwater detention instead of just going in. This one, I wanted to show you that it doesn't have to be just used in wide open spaces, but also in areas that you would normally not think of. In this area, this was a buffer area in New York for a park. And it was highly urbanized, and there was lots of impervious surfaces contributing to this. But not only does it prevent it from going out into the water, but it actually doubles at a storm surge protection living shoreline. Okay. So just a quick minute or two on my company. We have worked all over the country, and we can find solutions based on different ecotypes, different elevations, different considerations for climate, such as Florida versus Washington or Maine. We have a lot of experience. In fact, we were established in 2001 on the East Coast, and now we have the San Diego headquarters up here, Imperial Valley, New York regional offices. We have about 30 staff, and we have already 12 different projects completed in the US and abroad in various countries. We've worked on some projects that are quite amazing, actually, in other countries to create wildlife areas or planting or wetland areas. So we have a ton of services that we offer in addition to just creating wetlands or stormwater bioretention strategies. We can do all these other things. And I suggest that you go on our website and Google us if you're looking for various natural resource innovative solutions. We are the ones to help you with that, but also even environmental litigation support, drone vegetation surveys. We pretty much do it all. This is our founder. His name is Mark, and he's awesome. And he has 30 years of experience doing this. And his restoration planning, again, has been used all over the world. So he can find a solution for you. In 2022, he won the National Wetland Award recipient, and that's me. And I am the specialist in phytoremediation. And I can definitely find you a solution depending on what you want or what your problem is. But if I can't, I'll tell you that as well. So I like to say that I'm available after this. If you want to contact me, if you have a question perhaps about a site, or perhaps you want to do some sort of stormwater bioretention retrofitting, we can talk about it and see if we can find an application that'll work for you. So I'd like to open this up now for questions, for those of you who may have them. Does anybody have a question?
Fantastic. It doesn't look like we have any questions in the chat, but if you have a question, go ahead and put it in the chat, or you can unmute yourself and ask Kat.
Yeah, I love to answer any questions. I think we covered a lot of material here. And again, you can always contact me if you have a question about a site. I appreciate that. So it always helps me to learn more by doing different sites.
Fantastic. Well, thank you everyone for joining us while we wait for any questions to come in. If you missed any part of this presentation because of technical difficulties or you had to leave early, it is recorded and is up on our website. In the next 24 hours, it'll be up there so that you can watch the entirety or share it with someone that you know would enjoy it. It doesn't look like we have any questions, so we might let everyone go a little bit early. But thank you so much, Kat, for presenting. It was wonderful. We always enjoy having you part of Stormwater Awareness Week. And thank you, everyone, for joining us. We hope you enjoy the rest of the event.
Thank you so much, Rebecca. All right.